Hello, welcome to this lesson of study of integral equations. Okay, so in this lesson, what we'll do is we'll go through some basic definitions of special types of kernels. Okay, so if you have not subscribed to my channel, kindly subscribe so that you can support this channel as well. Okay, all right, let's start. So we have a first kind of kernel to be the separable kernel. Okay, all right, so with a separable kernel, we say it is a kernel which can be expressed as product of two functions, one as a function of x only and the other as a function of t only. So let's say you have your function. If you can break your kernel k of xt, okay, in the integral equation to be some product of two functions like this. When you say product, I hope you understand, just multiplication of two functions. Okay, then you have a separable kernel. Okay. All right, so let's go ahead and pick an example of this type of kernel and see. So like I have here, the first one is k of xt equals x times t. That is this one. And you can break x times t as x standing alone, okay, multiplying t standing alone. And with this one, we say our g of x will be this and our h of t will be this. Okay. This is very simple, right? And if you have k of xt being equal to e to the x plus 2t, then from indices we can break e to the x plus 2t as e to the x times e to the 2t, right? And you can see that this is a function on x alone, that is our g of x, and this is a function on t alone, which is our h of t. Okay, so this is what we mean by just a separable kernel. All right, so let's go ahead and pick the other type of kernel, that is a degenerate kernel. With a degenerate kernel, what happens here is that you say it's a kernel if it can, or if it is able to being expressed as sorry, here is supposed to be as. Okay, so a kernel is said to be degenerate if it can be expressed as the sum of a finite number. This is very, very important, a finite number. Okay, so we know the end. It can be expressed as a finite number of terms, each of which is the product of a function of x only and a function of t only. So this is some way like summation of separable kernels. That is how I can describe degenerate kernel to be. Okay, so actually a separable kernel is some way somehow embedded in degenerate kernel. Okay, so like I said, if you can have a kernel that is a summation of terms or summation of functions together, okay, where each term is containing or consisting of a function of or a product of two functions which consist of a function of x only and a function of t only, then that is a degenerate kernel. Okay, let's pick an example which will help us get the basics. Well, okay, so let's say if I have k of xt being equal to cos of x plus t, how do I know that this is a degenerate kernel? Okay, this is the same as cos x. Okay, so you can see that this using the trig identities, this can be written as cos x cos t, okay, minus sin x sin t. Okay, now you can see that the kernel has been broken down into two parts. Okay, so I can say that this k of xt is the same as summing these. Okay, is the same as k1 of xt plus k2 of xt, where my k1 of xt, okay, k1 of xt is equal to cos x cos t, and then my k2 of xt is equal to minus sin x sin t. Okay, so if I sum these, I'll get that back. So if you have a kernel that can be broken down into this summation of that, and you can see that within each sum or in each sum, the sum consists, or the terms consist of product of functions of x only and t only. So you can see that this one is just a product of x cos x, a function of x, multiplying a function of t, which is cos t. And the same thing happens to this one, sin x multiplying sin t. So they are just functions of g, that is g of x here, and this is my h of t, but there are series of them, or there are some of them. So the point that I said the finite number is very important is that you can see that it's just summation of two of them, and it's not an infinity sum or infinite sum. Okay, I hope this is cool. So that is the little explanation I can give you about degenerate kernel. So let's go to, I think, the last one, and then we have other type of kernel, the kernel of the convolution type and the rest, but at high level let's stick to this. Okay, so with a symmetric kernel, it's also another type of kernel. We say a kernel k of xt is said to be symmetric if it follows that k of xt is the same as k of tx. Alright, meaning is that you just interchange the variables. Okay, so the first example, this one, k of xt being equal to sine of xt, or sine x plus sine of x plus t, and I think to prove that this k of xt is equal to k of xt is equal to sine x, that's sine of the expression x plus t, rather, we have to prove that this is the same as k of ts, and then this become a symmetric kernel. K of ts simply means that just wherever you see x, you interchange it with t. Okay, so k of xt is equal to sine of x plus t, then k of ts will be equal to sine of, wherever I see x in this, I just change it to t and become t plus x. And t plus addition is how do you call it, commutative, so this is the same as sine of x plus t. So this becomes very simple, right? This is very simple, and it shows that indeed this kind of k of xt being equal to sine of the expression x plus t is symmetric. Okay, now let's look at the other one. The other kernel was k of xt equals xt, and this is very, very simple. It's just self-explanatory example. Okay, so this one is the same as, if I find my k of tx is the same as tx, like this, and this is the same as xt, which means k of tx is the same as k of xt, making it a symmetric kernel. Okay, so that is the little explanation, or the little idea I have about kernels. And in our next lesson, we'll be needing these type of kernels to solve questions. Okay, and I think that is why we were supposed to come through this video and then talk about some special types of kernels. Okay, thank you, and kindly subscribe to my channel if you have not subscribed. Like my video, comment, and also share it for others to benefit as well. See you next time.